So can I start my talk?
Sure, sir.
Please.
So, okay. I would, this is really a very good gesture from Dayanand Sagar University. They are hosting a very big national conference. Thanks to Vice Chancellor Dr. K. Palasubramaniamurthy, Vice Chancellor, Management of Dayanand Sagar University, Chairman Dr. Vaibhav Mishram, Dr. Sara, and my dear colleagues and my dear participants and listeners of my talk. So once again, I thank all of you having been given a chance to give my invited talk in the keynote talk in this international conference. First of all, because of some technical sag, we are not able to connect to each other. Now I'll start with the things. I think Vaibhav is on. Who is changing the slide? Vaibhav?
Yes, sir.
I'm changing
Vaibhav?
the slide, sir. I'm changing.
Yes, sir.
Yeah, okay, you can start. Okay, now I would like to give some outline about it. We go to the previous, okay, okay, it's okay. So first of all, I'd like to give some introduction. Next slide. I would like to give some introduction to technology, but earlier it was a new technology, but still a lot of things to happen in this one. I'd like to give some complications. And also, I'd like to give what is photonic crystal ring resonator. Design and modeling of PCRR, temperature, FTDD method, simulation result, analysis of fluoride contents in water using PBG sensor, and finally conclusion. Go to the next slide, Dr. Vaibhav. Next. Yeah, looking at this one, this butterfly, you can see what is photonic band gap. I'm just sharing with you. You see the color on the butterfly. That means to say that the colors perceived by eye is nothing but change in refractive index of the butterfly wings. What I tell you, it's a periodic structure. So what will happen? It is just like a band reject filter in our frequency domains. Low frequency components are passed, high frequency components are cut off. Only the middle high frequency are also passed. Only the mid range is stopped. So in this photonic band gap, when the mid range is stopped, the wavelength is stopped, reflection will occur. Because of the reflection, we are going to see the color on the wings of the butterfly, as well as like some peacock or parrot, colors of the wings of the parrot, like that. It's a naturally occurring phenomena. So we have explored out of it how we can manufacture. Okay, photonic band gap crystal is good. Photonic band gap crystal is a structure that can manipulate the beams of light the same way semiconductor can control the electric current. Okay, and so semiconductor connector cannot support electrons of energy lying in the electronic band gap. Similarly, photonic crystal cannot support photons lying in the photonic band gap. There is electronic band gap. I already told photonic band gap. So photonic band gap, once again, I am telling you, because of reflection we are going to get, because certain bands are not passed. That's the reason why we call it as photonic band gap. Okay. So definitely there are some things which is available. Optical fiber, you know that one. It is a part of also you can have you can send the light from one end and you can receive the light from other end. So the last one which I am going to discuss is photonic crystal waveguide, the last one. Okay, so where we have simulated, and I'll show some of the results also. Okay, next. 1 second. There is some power failure here. Okay. Hello.
Yeah, we are able to hear you, sir. But a little bit voice is breaking.
So okay, now we will go to the next slide.
Now video is also coming. No problem. Video, audio, both are on.
Yeah, next slide. So then dielectric waveguides are large in size, and also the most important thing is there will not be any what you call 90 degrees bend is not possible. Okay, 90 degrees, right? Hello, audible?
Yeah, you are audible, sir. You are audible.
Clarity is there. Voice clarity is there. Vaibhav?
Yes, sir. You're audible,
Yes, sir.
sir.
Everything is fine. Yes, sir. You speak, sir.
Everything is fine. You proceed. Audible, sir.
Okay, okay. Then photonic crystal, right? We cannot bend 90 degrees because light will not be confined into the wavelength. It will escape out of it. Okay, next. Next.
Yes.
Next slide. Blank is coming.
Yes, blank one.
Hello. Yeah, you can see. This is animated. So what we could do is it is just like to understand. There will be optical source and optical detector. We want the light to.
Sir, your voice is breaking. Sir, your voice is breaking.
On camera.
Voice is breaking. Once again, let's come back once again.
Your voice is breaking, sir.
Just a minute. Now I'll start. Second. First slide. Not the next slide. Next slide. Next. That animation is there now, please. Hello.
Yes.
Yeah.
Sir.
Okay. You stop there. Okay. So anyhow, this animation you are not able to track. See what we are doing. One of the thing, optical detector is there, optical source is there, and in between some blood sample is there. Blood sample. Okay. So first of all, actually you have given the final this one PowerPoint, but before to that one there were animation of this one only. But what's happening here is, in fact, already we have got one curve for normal blood that is in green color. But if you look, yeah, this is you have gone to fluoride contamination. Let it be here only. I mean, Vaibhav?
Yes,
Hello?
sir.
Yeah, let this be there only. Animation is not working from your system. You can see, first of all, we are having one water, and from optical source is there, optical detector is there. When pure water, we are getting some wavelength. You can see in the blue light, in the bottom, you can see the blue spectrum. So next, go to the next. No, there only be there. There only be there. There only. So, and also we pass the light through a contaminated water. You will see you can see the change in the wavelength shift, and it is becoming red. Okay, it is not red actually. For the purpose of understanding you, I am doing this one. Okay, next. Oh, next.
Yes.
Yeah, now I already given the photonic crystal. Next. Next. Introduction. Okay, I have already given few introduction about it. There are two. Go to introduction. Yeah. There are two types of photonic crystals. One is, of course, one is rods in certain substance and holes also there. There are two different types of periodic variation of. Because of this, we are going to get periodic variation of diffractive index. Next. See, here you can see 1D. 1D means there is a change in refractive index in only one direction. You can see that one. But in 2D photonic crystal, there is a change in refractive index periodically in two-dimensional. In three-dimensional, you can see in all the three dimension X, Y, and Z coordinate system, there will be a variation of refractive index. Next, okay. So one-dimensional, two-dimensional, and three-dimensional. Next. Yeah, this is what the structure. So there are actually you can see the rods in air. That is one of the structure which we are seeing, and holes in some material. So that I am going to discuss. So from this one we can measure temperature, pressure, or anything like infection. Everything we can measure using these kind of sensors. Next, I'll show the few application of it. You can see now. Earlier, whatever I have shown, there are no defects at all. Now you can see there is red line is there now. If I remove the red color rods, the whole line, it will become line defect. And if you remove only one rod, that is yellow, then we have a point defect. You can clearly see in this one. That means if the total line is removed, it is rods in air. One line is removed, it is a line defect. If one rod is removed, it is point defect. Next. So this is a point defect you can see. Next. Next slide. Yeah, you can see here. No, previous. 2 slides. Point defect. Previous. Just here. Yeah, be there only. This is a slide which. So now you can see there is no defect. You can see in the left, that is periodic variation of refracting in the left one. In the right one, we have shown photonic band gap. If you pass the light through this periodic structure, you can see there is a pass band on lower wavelength and higher wavelength, and in the mid band, that is photonic band gap, you are not allowing. This is not allowing any wavelength to pass through this particular stop band gap. Next. The same thing, the previous one, the same thing. So what I have, no, just go to previous slide. Yeah, you can see here the red line which I have shown, only one rod is removed. Only one rod is removed. You can see in the spectrum that only one wavelength is being passed in the pass band. You can see remarkable, just one spike. So that is where we are exploring this point defect or line defect to find out many things. Okay, next. Yeah, this is a line defect. Next. Yeah, now what is this PCRR? That is photonic crystal ring resonator. We can construct the same photonic crystal ring resonator for this ring resonator on photonic crystal. It has got a upper bus and a lower bus. In between that one, there is a ring resonator. So if you pass the light through port 1, if it is resonant, it can come out of port 3. It is completely. That means if you give the light input to the port 1, if it is 100% resonating, you will get the output at port number 3. So it is completely what I am telling. It is a micro ring resonator. So the same structure we have developed using photonic crystal. You can see now here. So in the photonic crystal, you can see you are giving the, just be there on this slide for certain time, Vaibhav. Then I will tell you to change the slide. Okay.
Sure.
Please, please look into this wave. This is the structure. It is a photonic crystal ring resonator. It has got only one bus on top of one circle below. That circle is ring. So you can see that one. Both, it is a line defect. First of all, upper one is line defect, and the ring is also line defect because we have removed the rod in the form of circle. That's the reason we call it as ring resonator. Okay. So input port is A and output port is B. So there are rods. How in this figure only I am going to explain many things. You first of all, what I tell you is you fill this with, for example, I'll be giving you 2 examples. For example, we'll take. I have already given in the previous slides that was not changing. I have done some very good animated slide. Unfortunately, it was not changing. So now give the input. You fill this with pure water and pass the laser beam through input port light. You are going to get output at port B. So you will get one wavelength. So that wavelength may be for pure water. Next, you fill this up with the contaminated water, maybe different kind of fluoride contents. Then you are going to see a different wavelength. There will be a wavelength shift from pure water to contaminated water. So depending upon the shift in the wavelength, we are going to tell what type of content. So it may be different kind of fluoride content is contaminated in the water. Or if you want to say, if you want to think about a urine sample or blood sample, if someone is infected, first pass the analyte. Analyte means good blood through this waveguide, and you are going to get one particular wavelength. After that, if someone is infected with any disease like virus or bacteria, of course we have done for COVID-19 also. That also in the coming slides you are going to see that one. So then, when depending upon the nature of the infection, you are going to get different wavelengths. There will be a wavelength shift. Each bacteria or virus will have different refractive indices. Because of refractive indices, we are going to have change in the wavelength. That is, change means shift in the wavelength. So that is a signature. For example, we have done for E. coli, Bacillus series, COVID-19. Then in the coming slides, I am going to show that one. Next, Vaibhav. So once again, what is the advantage of MOEMs? MOEMs are thermally, they are stable alignment. Most important thing is thermal stability, faster response, and comparative. It is compatible with fiber optic cable. That is most important thing. That means you can give the input to the fiber optic cable light, and you can get the output to the fiber optic. So there are different applications. Next. So I don't want to go to the history. Next. Okay. So now previous. Yeah, here we can develop directional by using photonic band gap. We can develop directional couplers, Mass-Zander interferometers, Bragg gratings, and micro ring resonators. We have worked on Bragg gratings. We have worked on micro ring resonators. We have worked on directional couplers. Okay, next. Yeah. Now design and simulation. This is one of the thing which we have done in our lab. Crystal-based ring resonator for temperature measurement. Okay, next. We just go through it. We'll see directly next. Yeah, stop here, stop. Before this slide. One slide before this one. No, before one slide before. Yeah. So what next? Yeah, stop here only. So we require what is known as finite difference time domain method for calculating, for measuring anything in photonic crystal. So we are really dependent on FDTD method to simulate photonic crystal structure, and perfect match layer is placed as absorbing boundary for the condition. The technique is extremely versatile. Okay, next. So this is the thing. So hello, previous. Yeah, you can see the lattice structure. You can see EX, EY, EZ, HX, HY, HZ. There are different components of electric and magnetic field in X, Y, and Z coordinate system. Next. Previous. So I don't want previous. Next. Just next. Yeah, stop here. So the time varying electromagnetic fields obey definitely Maxwell's equation. Then we need to find out the solution of Maxwell's equation. That is possible with our FDTD method. You can see there are basic 4 equations of Maxwell's equation: del dot H, R, and the function of R and T, and del cross E, del cross H, del dot E. But here you can see rho and epsilon. See here, epsilon is permittivity, mu is permeability, sigma is conductivity. All are variable with respect to R. That is a challenging thing here. The next. So these are all the coupled equations. We don't want to move into the mathematics. So earlier we were using MEEP R, freely downloadable software which is available now also MEEP. It was done by MIT Electromagnetic Equation, done by MIT Lab USA. But we have in our lab, we have set up our own lab. In that one, earlier we were using MEEP. Now we started using what is that numerical software. Okay, numericals. Next. Of course, it is a paid one. So next, go to the next. Go to the next one. Next. So let me not focus on temperature sensor. So I'll go to the next application. The next. Yeah, now. So this is most important. Previous also that was a application of measuring temperature. Now we are measuring fluoride contents in the water using photonic based biosensor. Next. Previous. Next. Next. Yeah, stop here, stop here. See, in our day-to-day life, everybody will dig borewell to get water. But unfortunately, some of the borewells will be contaminated with contaminants like calcium fluoride. So because of calcium fluoride, dental fluorosis will occur. Because of cesium fluoride, nausea, vomiting or diarrhea and bleeding around coma or even to death. Then potassium fluoride, different things, depression, muscle weakness, heart rhythm disorder and confusion. Like that, strontium fluoride will have some different effect. Lithium fluoride will have different side effect. What we can do here, we can clearly tell what type of water is contaminated with which type of fluoride content. So calcium fluoride will have its own wavelength. Cesium fluoride will be having different wavelength. Because of a change in the wavelength, we are going to get change in the what is that wavelength shift. Okay, next. So next. So this also done by MEEP. Okay, MEEP and MATLAB. For plotting, we are using MATLAB. Like, just go next. Yeah, stop here. Previous. Just one slide previous. Yeah. So here you can see the power. Hello. Next. Be there in the slide only. MEEP algorithm. MEEP is a time domain tool, and MEEP is simulation package for computation of transmission reflection spectra. You can see the power is equal to what is that integration of E cross H d square x. Okay, next. Okay, next. So these are all the simulation results which I am going to show you. Next. There is one animated slide. Next. Yeah, animated slide. It's not running. Previous. You can see previous. Next. Yeah, stop here. Just previous. Just one slide previous. Yeah, stop here only. So you can see light is entering from the left side of this ring resonator, and it is going through the bus, and a portion of the light is being coupled with the ring resonator. Next. So you can see the transmission spectra of a pure water. You can see only one peak you can associate it with this one for pure water. That is the signature of the pure water. Next. So calcium fluoride, you can see the maximum frequency will be shifted from the pure water. Cesium also, you can see the peak is occurring in different place. That is the signature of cesium fluoride. Next. You can see lithium fluoride and also potassium fluoride. Next. You can see for pure water, the peak frequency is at 0.2955, but for calcium, it is 0.2919. If the water is contaminated with calcium, you are going to get shift in frequency of 0.0036. Like that, supposing say another potassium chloride, then the peak frequency is 0.2727. It is the potassium fluoride signature. The shift in the frequency is 0.0228. So because of the shift in the frequency, next we will get the shift in the wavelength also, because wavelength and frequency are once again related. Next. Yeah, next. Yeah, I can see previous. Yeah, here stop here only. Transmission spectrum for pure water of wavelength shift. You can see for this particular case, for a pure water, you are going to get one wavelength. Next. You can see calcium fluoride and cesium fluoride. You are going to get different wavelengths. For calcium fluoride, you are going to get certain wavelength. For cesium fluoride, you are going to get certain wavelength. They are signatures. Next. Lithium fluoride also like that. Potassium fluoride also like that. So let us see the table. Calcium fluoride. You can see for pure water, the wavelength is 3.384. So that is the signature of the pure water wavelength. Calcium fluoride, if it is contaminated with calcium fluoride, the wavelength shift is 3.426 and the shift in the wavelength is 0.042. Once again, I am telling you the calcium fluoride, the signature is 3.426. Cesium fluoride, it is 3.66 and shift in the wavelength is 0.276. So depending upon the shift in the wavelength, we are going to tell which type of fluoride content is there in the water. Okay. Next. Next, Vaibhav. Next. Next. So this is the total spectra, including everything: calcium fluoride, cesium fluoride, everything. Okay. Zoomed version no need not be there. Next. Okay. Okay. Next. 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 Be there in the conclusion only. So we have developed this kind of thing very nicely in our lab, and these two previous sensors, the temperature and fluoride sensors, they have won international in the best paper award for these two work from our student. One is Malika and another is Girijamba. Okay, so these results they have done very well, and it has been published in very good journals like IEEE and elsewhere also. Next. So these are the publication out of this work. So next. Yeah, once again, this is the third one which we have done in our lab: design and modeling of photonic crystal nano cavity based pressure sensor. You can see in the top figure A. In the figure A, this is a photonic crystal line defect waveguide. Top is silicon layer, and you can see the outside, and you can see photonic crystal line defect waveguide. You can see there in the A figure A. But you can see in the right figure C, the fabrication details of it is silicon. The bottommost layer is 450 micrometer. Middle one silicon dioxide is 3 micrometer, and on top of the layer silicon is 220 nanometer. So you can go to the figure B. In the figure B, you can see applied pressure. You can see in the A figure no application of pressure, but in figure B, applied, because of the applied pressure, there will be deformity because of pressure. When there is a deformity in the structure, you will get refractive index change in the refractive index. Because of change in the refractive index, you are going to see what is known as change in wavelength. So for each value of pressure applied, you are going to get different wavelengths. Okay, next. So these are all the things which we have taken. A is the radius of the hole, it is 1 micrometer. R is equal to 0.199 micrometer. Height of the stab is 220. The pressure can be applied, can be calculated using P is equal to A omega rho C, where P is acoustic pressure, A is displacement in amplitude, omega is equal to 2 pi RF. So sigma is specific density, C is speed of the light. Okay, the pressure is proportional to the displacement. Next. So this is what actually we got simulation from nano cavity pressure sensor, the thing which I am dealing now. Next. So these are transmission characteristic spectra. Next. The summary of the work. Sensor previous. The sensor is constructed with two-dimensional photonic crystal waveguide, which is coupled with nano cavity sensor. Okay. The sensors can be used in application requiring high accurate sensing results. The frequency can be mapped by shift in the displacement by using the pressure formula. Okay. So this is also one of the another type of sensor we have developed in our lab simulation. Photonic crystal based mechanical sensor on silicon on insulator platform. Okay, next. So you can see here in the first figure, you can see figure 7. In the first figure, you see this is a ring resonator, hexagonal ring resonator. Second one is the cross sectional view, and third one you can see how you can see the structure. Okay, once again, structure cross section is air by 220 nanometer thick silicon air with refractive index 3.46 and 1 respectively. Lattice constant is 420 nanometer. Air hole diameter radius is 120 nanometer. Slab thickness is 220 nanometer. The filling ratio is 0.3. assure sufficient amount of photonic band gap in TE mode operation. Okay, next. So these are all the different value we are going to get transmission spectra. See the variation in the wavelength clearly. Okay, next. Hello. Vaibhav? Previous. Yeah, be there here for one. Previous. Next. The graph. Next. No, next. Please show the graph. Next. Be previous. Just previous. Yeah, be here only. You can see. Just previous. Yeah, be there. Here only. You can see applied pressure is 4 gigapascal, 3 gigapascal, 2 gigapascal, 5 gigapascal, 1 gigapascal, 0 gigapascal. So depending upon the applied pressure, you are going to get different shift in wavelength because there will be change in refractive index. Next. So the totally what we have seen in this one, a shift in the wavelength or ratio of micro displacements in the proposed sensor up to a quality factor of 1495 and high sensitivity factor of 1200 RIU. What in this one which I would like to stress you is if you are using a resonator to get high sensitivity, you should have high Q. Q means quality factor. Okay, next. So design and analysis of photonic crystal based MZI based pressure sensor. Next. So this is another I told you we have developed different kind of sensors. You can see here Mach-Zehnder interferometer. Figure 12. Figure previous. Be there only. Previous. Next. Be there only. Don't change. Be there only. Okay. Just one slide previous to this one. Mach-Zehnder structure. Figure 12. Be there in figure 12 only. Okay. Okay. It is Mach-Zehnder interferometer. Okay. Be there here only. You can see there are two. There are two arms. One is upper arm and another is lower arm. So what we are doing is here is by using the Mach-Zehnder principle, we can see left is blue color and right is some gray color. Okay. So what we are doing is once again we have taken the same thickness material, silicon 450 micrometer, silicon dioxide 3 micrometer, and silicon 220 nanometer. So what we are doing is, and also the ratio, the refractive index is 1 or 3.46 and 1. Okay. Lattice constant to 420 nanometers. Radius is 135 nanometers. Thickness is 220 nanometers. You can see this structure clearly. The left portion is blue. And when we are applying pressure on this diaphragm, this Mach-Zehnder diaphragm, definitely without applying the pressure, you are going to get certain wavelengths. And after application of the pressure, we are going to get certain wavelengths. The gray area of this one is it is the normal arm. So that is the reference arm. The left blue is there now. That is the sensing arm. Okay. Next. We got reasonably good results for this one. And in this one, you cannot be we have gone for stress analysis. You can see the stress analysis. Next. These are all the graphs of this we have done using numericals. Next. For displacement analysis. Next. Result analysis. Then you can see the transmission characteristic. Previous. So this is the most important thing. You can see here for each value. Previous. Yeah, figure only. Figure 18. Figure 18. You can see first one is 0 megapascal. It is coming at around 1.56 micrometer. Okay, wavelength micrometer. You can see in the right side, different application of different pressure. There will be a shift in, there will be change in refractive index. Because of the change in refractive index, you are going to get change in the what is that one wavelength. So, for example, last one you can see for 6 megapixel megapascal, you are going to have 1.564 micrometer, and previous to that one is 5.4 megapascal. So, depending upon the applied pressure, you are going to get different value of refractive index. Because of change in refractive index, you are going to get different wavelengths. Next. So these are the result analysis. You can see quality factor is 7047. It's a good quality factor because Q should be very high for getting good what you call sensitivity. For 0, it is Q factor is 7047. Wavelength is 1550.37 nanometer. You can see if you apply 0.6 megapascal, the stress is 0.1987, but you will have change in the wavelength is 1551.51 nanometer, and you can see there is a change in wavelength from when compared to 3.46. For 0, it is 3.46 refractive index. The wavelength is 1550.37. For 0.5 megapixel, the refractive is changed from 3.46 to 3.46307. Wavelength is changed to 1551.51 nanometer. For example, go to 3 megapixel, you can megapascal, 3.47535 is the change in the refractive index. Because of the change in the refractive index, you will get change shift in the wavelength. You can see 1556.84 micrometer. Like that, you can calculate. Next. So this is a summary which I'd like to tell you. The quality factor of 7000 we can able to achieve. This ring resonator we can go for 30,000 also. So we need to do some more exercise into it. We can improve on the quality factor. Next. So this is another one, resonator for detection of glucose concentration in urine. Next, micro ring resonator. You can see here clearly, for normal sugar, you are going to get somewhere around, you can see the figure that is magenta color or what you call. But if there is some 0.625 gram per deciliter is contained, then you are going to have shift in the wavelength. Why shift in the wavelength? For different value of glucose level in the urine, there will be different value of refractive index. Because of different refractive index, there will be change in wavelength. The last one you can see 15, the black one. So by the frequency shift or wavelength shift, we can definitely tell what percentage of quantity of glucose is there in the urine sample. Next. 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 So urea, okay, can go to the next one. Pressure, another pressure sensor structure. Next. Pressure sensor structure. Next. Next. Yeah, we have done another thing. Oscilloscope series and COVID-19 detection using photonic crystal biosensor. The same structure can be used. Next. So you know that coronavirus is large, roughly a spherical particle with surface projections. The diameter is 125 nanometers. The envelope is 80. The diameter of the envelope is 85 nanometers, and spikes is 20 nanometers. You know that is a protein spike. That is the one which connects or which adhere to the lining of the lung tissues. Next. So this is a COVID-19 virus structure. Next. The next. Bacillus series. Next. So next. You can see previous. Okay. Next. You can see the, okay. Next. Next. So next. Next. Oh. Next. Okay. I think previous. See different previous. No, the ring structures. Go to the ring structures. Previous. No, next, not previous. Next. Stop here. You can see this is a ring resonator structure. This is how it works. Next one. Yeah, I can see. Figure 7, split ring resonator. You can see a small portion of the ring is split. Figure 8 is a double ring resonator, and this is asymmetric. So 2 rings are there in between 2 buses, but one previous ring resonator. Yeah, in one of this one. Next. Figure 7, 8. Yeah, 9. Figure 7, 8, 9. Hello. You can see here. Can you see here? Figure previous. Yeah, be there in this one only for 1 minute. Split ring resonator. Second one is figure 8 is 2 rings are there. This is asymmetric ring structure. And figure 9 is double ring and figure 9 is symmetric one. Okay. Figure 8 is asymmetric rings. Figure 9 is symmetric ring. Okay. Next. Applications, you know that one. I already told. Next. Yeah, you can see different structures how we have made. You can see from the top view of this one, rods in air structure. And this is DFT amplitude simulation diagram. Okay, good. Next. So it is a double hexagonal ring resonator. Next, not previous. Next. Result analysis. Next. Go to the, I think, last slide now. Yeah, last slide. Next one. Oh, okay, be there on this slide. So stop here. Go to the last slide. Thanks slide. Yeah, thank you very much. Once again, I would like to conclude my talk. So in this totally, I have taken you to the various type of photonic band gap semiconductor photonic band gap crystal sensors. All the things we have done in our lab only. Right now, under me, 35 students, UG, PG, PhD are working in our lab, in photonics lab. And we are getting reasonably good results. But unfortunately, we are not able to fabricate. So fabrication needs to be done in IAC. And to be precise, if you want this thing to be what you call reality, we need what is that one is on a fabrication facility, very good fabrication facility. It can be done only in abroad. I'm telling you, this is the whole concept is lab on chip. What do you mean by lab on chip? We need not have to go to the pathological lab now. So on a small chip, if you pour water, if you pour urine, if you pour what is that one blood, you can definitely measure what type of water is contaminated, what type of bacteria is invaded into the blood, what type of bacteria or virus invaded into the blood and urine. You can clearly tell. So this is what the application of biological sensors. And another application is pressure sensor. Pressure sensor also we have done it. So once again, there are many medical applications of pressure sensor. This can be used in what is called measuring pulse, blood pressure, intracranial pressure, so etc. And also it can be used to measure normal day-to-day life pressure. And also, apart from medical applications, we have one more thing, structural monitoring. You know that civil structures, bridges and all those things, they should be monitored. How much pressure it is withstanding, what is the vibration it can withstand. For all those things, we need what is known as pressure sensor, and in turn it is a vibrational sensor. So with all that one, I think Am I, now I think Dr. Sara is sharing my screen. Am I right? Hello?
Hello, yes, sir.
Yeah. I think now I am done with my, what you call, presentation. Anybody is having doubt, you are most welcome. Sorry for the inconvenience. There are a lot of things happened in today's talk because of technical stack. So I am not able to concentrate much on my topic, but anyhow, I could able to deliver whatever I wanted to do it. I have delivered. Any questions from the audience? I'm ready to take up.
Any questions from the audience?
And also one more thing I would like to tell you, those who want to do their projects like BE and ME, and also even PhD, our lab is available. We have got very good lab in our department, which are nominal charges for any research for the students. And those who are interested may kindly approach me directly. I have, I think you know my email ID. It is given in the brochure, and also I think you can directly contact me over email pcs@mcehasan.ac.in. Okay, madam, and I will handing over to you.
Yeah. Thank you, sir. Thank you, sir, for such an informative presentation. And you have shown light on various aspects of the photonic sensor. Your talk on the photonic crystal ring resonator temperature sensor and the use of ring resonators for various applications was also very interesting. So all the participants for this conference have been greatly benefited. Thank you very much, sir, for sparing your precious time, sir.
Okay, thank you. Sorry for the technical stack.
No problems, sir.
Thank you very much, sir. No
Thank
problem.
you very much, sir.
Thank you, doctor.
I now request